Okay, so my talk is about using Datalog as a foundation for probabilistic programming. So I know I have to define some things. So why probabilistic programming? I think a fairly common theme today, starting with Carlos's talk and Joe's talk and Chris's talk, is that building smart software is hard. There was a recent DARPA solicitation asking for people to help them solve the probabilistic programming problem for advanced machine learning. And in the solicitation, they said, unfortunately, effective machine learning requires Herculean efforts by highly trained experts. So the ambition here is to make the possible easy and to make the impossible possible. So what is probabilistic programming language? I haven't found a very crisp definition for this, but I did find one in a PhD thesis here by Serge Bott. And he defines a probabilistic programming language as a language that lets you express optimization problems, lets you express probability density functions, lets you make arbitrary transformations of random variables, and that it's a formal declarative language. And he gives a table here of languages invented by the PL community and the ML community that meets some of that criteria. So how is such a language implemented? DARPA proposes the following layering. So the first layer are the applications themselves, the problems that you're trying to solve that domain experts use. One level down is the programming language itself and the tools that go with that. Next level down is a series of solvers, domain-specific solvers for different aspects of the problem being solved. And then finally, there's a computation layer that has to support current and emerging computational models. So how are we realizing this vision in logic blocks? So we're building a database, a smart database for smart applications. So unlike some of the other speakers today, we are trying to build a database that supports OLTP, OLAP, and data science use cases. And that's fundamental to making something difficult easy, is that you have to eliminate accidental complexity. And if I have to use a specialized technology component for the optimization part of my problem, the machine learning part of my problem, the graph part of my problem, the bookkeeping part of my problem, and the BI part of my problem, I'm not eliminating accidental complexity. Okay, so we're going for a one-size-fits-most approach here. So the programming model, the programming language we use is called LogQL. It's based on Datalog in the same way that functional programming languages are based on the lambda calculus. We don't work with a lot of people. We work sort of in close partnership with a few large enterprises, but they are pretty large. The aggregate revenues of the companies we work with exceeds $150 billion. So it's not quite Walmart, but it's about, I don't know, a third or a fourth of Walmart. Our company is made up of mostly of engineers. So we have 37 engineers, 23 have PhDs, 6 are former professors. So me and 2 other people are not in the engineering camp. Okay, we do most of our work in the retail industry right now. But we're looking to find 1 or 2 more partners to work outside of retail. So for those of you who don't know logic blocks or have never seen logic blocks, I'm going to break with long-standing logic blocks, Datalog tradition here. Usually if you see anyone talking about Datalog, they start with an example of how to compute ancestors. So given the theme of today and the importance of triangles and click problems, I'm showing you a little bit of Datalog to compute the triangles. So if I have an edge relation, I'm basically computing, I want everything A is connected to, so A is connected to B, A is connected to C, and B is connected to C, will give me the triangle of ABC. So why Datalog? So I don't have a PhD in Datalog. I don't have any reason to be biased towards Datalog. In fact, when we were sort of looking into this, I wanted to like what the cool stuff. I wanted to write like Haskell or functional programming languages like ML, or heck, I would have settled for Lisp. You know, Datalog was not only it wasn't sort of a current or cool choice. It was actually a very uncool choice. It was sort of discarded as a useful area of research in the mid-90s by the database community. But we picked it because its usability features. It's very declarative. I can take a Datalog program and sort of shuffle it around in any order. It still means the same thing. It's very first order. I don't have to think about functions, passing functions to functions. I don't have to think about building data structures using cons. And it supports a very natural incremental computation, so we heard about earlier as well. It's very expressive without giving you too much rope to hang yourself. So you can capture complexity classes like p-time and np and so on with different fragments of the language. But you can't write an infinite program accidentally. And there are attributes of the language that makes it really easy for us to offer full ACID with efficient and full serializability. And then the final point is around performance. Datalog emerged from the database community, and the database community cares a lot about a memory hierarchy, which is really important for performance. Datalog has a fragment that's very, very parallelizable. And again, the semantics of the language, what your program means, is independent of how you solve it. So, to give you sort of an example of the efficiency and the scalability here, because we're a database company, the first thing we wanted to do is measure our performance relative to other databases. Very common choices today are in-column stores, come in two flavors, the in-memory flavor and the not in-memory flavor. The darker blue bar here is in-memory column store made by a large German company. I don't know if you can see that. Yeah, we can't see the last one. Okay. And then the other column is not an in-memory column store. That's you can get from your favorite elastic computing infrastructure vendor. As you can see here, this is a log-log scale. I won't waste your time with the details, but if the not in-memory one got to the point where it can do a graph with 10 million edges, but it did in 19 hours what we did in 5 minutes. And the in-memory one blew up after 100,000 edges. And my colleagues were not happy with me showing this chart. They asked me to animate it with a dramatic explosion effect like this to show that the in-memory system blows up. Okay, so how do we get this kind of performance and out of a general system for a specialized graph query? Well, you have to rethink query evaluation a little bit. I don't have time to get into the detail, but you can find the detail in a paper that we posted on Archive called Leapfrog Tree Join by a colleague of ours, Todd Veldhuizen. And basically, it's sort of, we part ways with relational algebra. So we're rethinking the fact that relational programming has to ultimately map to relational algebra, and Leapfrog Tree Join is really a select, project, union, difference, join algorithm. Okay. This work was followed up or built on the breakthrough work of Chris Sri, who spoke earlier, where they proved that there exists an implemented a join algorithm that is provably worst case optimal. So a quick intuition on why that works. So imagine we have 3 tables, each has 1 million records in it. If you're doing relational algebra, you have to do a pair of tables at a time. So I have to join A with B, or B with C, or A with C, and in the process, I generate a temporary result. So in any order I pick here will generate a temporary result of about 500,000 records. Okay? But if I do the join K-way, I don't have to do any work because the result is empty. Okay? So hopefully that helps a little bit with intuition. So does logic blocks work for graph problems other than the n-click or triangle problems or 4-click problems? So again, we're learning about the space. So we picked 2 graph databases at random. Let's call them graph database N and graph database V. And we picked a benchmark at random as well, the Lehigh University benchmark suite. And we ran the suite on all 3 databases. And we're surprised really that we did fairly well in that benchmark. The thing to note here is a lot of times people motivate the need for a graph database and in comparison to relational databases, as they say, for queries where you start with a specific node and then navigate from there, those queries will slow down as the size of your relation grows. And as you can see here, for a lot of these queries of that type, even though the size of the relation is growing, the query time is not growing. Okay, and this chart shows basically the aggregate time for all the queries together against 2 specialized databases. And just to kind of give you a sense of logic blocks for this class of problems against column stores, row stores, and graph databases. These are the results we measured for 3 clicks, up to 10 million edges, 4 clicks, and 5 clicks. Okay? So pretty happy with this result, given that we didn't design our system like, I would say 6 months ago, I didn't know what a click was. Okay? So this was nice to see that the performance was good. Okay, so in our world, again, we're trying to increase data scientist productivity, and so it's important that when we do work, we be able to sort of update our assumptions about the data or update the data and not start from scratch again. And so it's really important for us to be able to incrementally update our queries. And as Joe said this morning, everything ends up being in a spreadsheet. A big distinguishing feature of a spreadsheet is if you have a lot of data in a spreadsheet and you change it, your spreadsheet model recomputes incrementally. You don't have to start from scratch, okay? And so if you're interested in how we do that, there's a paper also on arXiv on how to do that. We've broken with tradition in the database community by not using the DRAD algorithm. And hopefully very soon you'll see some publications from us on how to actually change the program itself and then maintain the results incrementally. Okay, this shows you for the 4-click benchmark sort of a 2-order of magnitude reduction in time when I update the data by adding 100 edges or removing 100 edges. I can recompute the view very quickly. And then the last part of how we do things quickly is by through automatic parallelization. Sort of the classic thinking on this is you shard data into big chunks and you place them somewhere and things work on the big data, but then you have a placement problem to worry about. It's sort of like taking big boxes and trying to fit them in a trunk. It's an NP complete, in a truck, it's an NP complete problem. So our model is more like pouring sand in a dump truck. You just sort of pour it until it fills up, and that's a much easier problem because you don't have to do scheduling at all. So for something like a TPCH query on 12 cores, you see each row represents a core, and the data is partitioned in small chunks there. And then again, when we finish consuming or allocating those small fragments, we're done. And so how does parallelization work in this? Last week, some of you know, SIGMOD was held in New York. The best paper from SIGMOD, believe it or not, was about out-of-core computation of triangles. Seems to be very popular these days. The work, obviously, the algorithms were hand-coded and hand-tuned, and several algorithms were presented in the paper, with MGT being the best and fastest. So given that we didn't even know about this work until SIGMOD last week, we just basically took some of the sample data, loaded in our system, and ran the triangle queries. And the column here on the right represents the results. Okay, now we cheated here a little bit in the sense that we ran this query using 16 cores, but it was automatically parallelized and got us within shouting distance of the best results. Okay, so in the few minutes I have left here, I'm going to just give you a few examples. So we support other solvers, not just leapfrog tree join. We support LP and IP, linear programming, integer programming solvers. We have some machine learning solvers built into the system from Ismion. And then we have prototypes built with solvers that use GPUs and so on. Okay, so in the 5 minutes we have left, let me tell you about 3 application areas. One is network optimization in the context of retail. We heard from Lee during the last talk that things like replenishment allocation matter to Walmart. Basically, Walmart and most retailers have to worry about getting product from a vendor to some kind of regional distribution center, to a distribution center, to a store, and that network is a graph. And typically, you have to track the inventory through that graph. This is a large graph because the time dimension is added to this. So every day, you have to think about making a connection from every one of those things to every one of those other things. And everything affects everything else. So old school thinking about how to solve this problem in retail is if I'm missing a product in a store, I just order it from the distribution center. I don't think about how that impacts anything else. But it's really, everything is interdependent, because if I allocate some inventory to one store, I'm implicitly not allocating it to another store. So these are really big LP, IP problems that we model. And if you have a relatively small retailer with 8,000 SKUs or products and 100 stores, modeling 435 days, you're talking about a problem that has 350 million variables. A slightly larger retailer might have, their problems might be 26 billion variables, and that's a lot smaller than what Walmart would have to deal with. Using the cloud and using sophisticated solvers, we can attack this problem. And again, we don't have time to get in the details of the models. These models are non-trivial. They're real-world models, and we've implemented them in less than 1,000 lines of logical. More importantly, they have real-world impact on the retailers that use them. And in retail, you have to worry about three things: your inventory, your real estate, and your labor. And anything you can do to reduce inventory and not lose sales is money in your pocket. So if I carry $1 billion worth of inventory and I can reduce that by 30%, I just put $300 million in my pocket. And that's the kind of impact we're having here. Real quickly, just one more example. This is a brick stream analysis or video analysis in the retail environments. So stereo cameras are installed in retail environments. And the stereo cameras then basically monitor the environment. And this is sort of like an Internet of Things kind of problem, in that they report back sample data about everything that's going on in the environment. And here is a view that shows all traffic down these 3 aisles in this large store retailer. But the traffic needs to be segmented in terms of employee traffic and customer traffic. And the way that you can tell who's a customer and who's an employee is by their behavior. So if a track if a person enters a zone that is designated as an employee zone, like behind the cash register, you can tag that person as an employee. And you can take sort of aggregate information like we have here on the left and segment it into customer traffic and employee traffic based on the fact that the employees are the ones that go behind the paint deck. Okay, and you can get really interesting data about where the traffic is in a store. It's just like clickstream analysis for a brick and mortar environment. And you can find out that 50% of the customers visit 50% of the store. You can also get interesting information about dwell maps. Okay, I had a little demo video to show you here, but I'm not going to show you. I don't have time to show you, but you can sort of see how simple changes in a store can really impact customer behavior. What you see here is that you have 3 end caps at the end of an aisle. This is prized real estate in a store. People pay to have their products put on an end cap, and that somebody at the store put a bunch of stuff in the middle of the floor and basically redirected traffic away from the end caps. Okay? The kinds of data sets that we're dealing with here on the low end is 250,000 samples per day. On the high end, as much as 9 million samples per day. And you're intersecting that sample data with the graph data that represents all the zones in the store. And basically, your analysis is what's the probability of someone visiting a zone after they've visited some other zone, or if they haven't visited another zone, and so on. And just real quickly, this is the kind of code that we have to write. It's very high level. It just maps the problem directly, and it performs reasonably well when you compare it to sort of standard approaches here. In this case, it's Postgres, but it's really important that we can do that sample zone intersection analysis very, very quickly. And it's really important that as new data comes in, we don't have to reevaluate everything from scratch. So this is where incremental evaluation really helps. Or if someone designs a new zone, we don't have to recompute everything from scratch. I had a last example on program analysis, but I don't have time for that, so I'll stop here. Thank you.